Alright. Okay. Okay, so we start. Okay. So sorry for last week. I couldn't do a live online class, but I hope you have listened to the recorded video. So it was about introduction to wind energy. Okay, so basically I will do a chapter by chapter. I will introduce a brief introduction about the some of the renewable energy technologies. So for this week, we will take a look at the fundamentals of solar energy. But for solar energy, it's bigger topic than it has more contents than the wind energy. Especially because me myself, I have done some research concerning this more on this solar energy. So this is more on my area. Okay. Okay. So we will see about fundamentals of solar energy and its applications. Sorry. Okay. So brief introduction. Okay. Basically, when we if we talk about solar energy, we have to understand first the process, of course, how okay, for example, the wind energy last time, it was about the turbine, the blades, the conversion of the wind, okay, the speed of the wind, which is the kinetic energy, to mechanical power or electrical power. Okay, so for this one, for solar energy, basically we know solar is the source is the heat. Okay, the sun, that causes the heat. Okay, and emit energy, transmit the energy to the environment. Okay, so basically when we talk about solar energy, we have first to understand the process, which relates a lot with the one of the types of heat transfer process, which is radiative. Okay, so actually there are three. Just to recap back, if you have learned in thermodynamics or mechanical, there are three types of heat transfer mechanism. Okay, so one of them is radiative or radiation heat transfer. Means that the heat is being transferred, the heat process is done by radiation. Another two is the conduction, which is mainly needs solid, okay, as the surface material. And another one is convection. Okay, so convection is mainly between fluid, gas, water, liquid. Okay, so for this one, for solar energy, basically it use radiation to transfer the heat, okay, the energy, okay, from the sun. So introduction, electromagnetic energy emitted by the sun is called solar radiation. So that is the definition, general definition of solar radiation means that the electromagnetic energy from the sun itself. So here we see this is the electromagnetic spectrum. Okay, tak boleh. Tak ada picture. Okay. Tak apa, punching pula. Okay, tak apa. Okay, this is the electromagnetic field spectrum. Okay, so from cosmic rays, the smallest one, to electrical power waves. So basically, this is the sun, the solar radiation use electromagnetic energy. Okay, so solar energy is said to be a bit cost in terms of cost, a bit more costly than compared to geothermal, hydro, and biomass, but it has lots of potentials. Okay, because especially we in Malaysia at the apa tu? Khatulistiwa. Okay, so we receive solar basically a lot more, okay, compared to at the northern hemisphere or southern hemisphere. Okay, so radiation fundamentals. So these the electromagnetic waves, okay, lambda. Okay, this is how we characterize to measure, okay, the electromagnetic waves. Okay, so it is characterized by the speed of light, which is c, okay, around about 3 to 10 power of 8 meter per second, the speed of light in a vacuum. Okay, I think that one you already know the parameter. Okay, next, thermal radiation. Okay, so okay, I introduced to you the about the radiative heat transfer, but we will focus more on this thermal radiation because it relates more with the solar energy. So thermal radiation is one type of electromagnetic radiation, electromagnetic wave heat transfer. So it measured the strength of these activities at the microscopic level. So of course, to measure the amount of thermal radiation, basically we look at the temperature. Okay, so for example, if in a house, okay, us in a building, in a house, so actually everything around us, every solid, or even us, the people, we constantly emits the thermal radiation. Okay, even us, we have energy in our body. Okay, so we can also transfer some heat, okay, to the ambience surrounding. Okay, the furniture, the plants. Okay, um okay, this is some of the light wavelength data, depends on the color. Okay, what I want to focus more on the black body radiation. What does it mean by black body radiation? Okay, basically black body radiation is the ideal. Okay, the ideal that it is an idealized body to serve as a standards against with the radiative properties. Okay, basically when we want to measure to characterize the amount of radiation energy, okay, we compare it with the black body radiation. So this black body radiation is like a reference. Okay, we want, if we want to compare the emissivity. Later on we will see emissivity, how we calculate the emissivity level. Okay, so so this black body, the role of the black body is to for us to as a reference, okay, to compare how much the amount of the radiation energy that the surface can transmit. Okay, so a black body is a perfect emitter, or the idealized body and absorber of radiation. Okay, so because a black body, it can as if it can absorbs all the radiation, okay, compared to a real body. Even we understand that if you wear a black t-shirt compared to if you wear white or any color, red, yellow, if you wear black color, okay, the heat, okay, the heat that we will feel, okay, we will absorb is more, right? So the black body is like we assume that the black body transmit and absorbs all the possible incident radiation from the heat, the sun. Okay, so the radiation energy, we write it as E. Okay, E, the black body. B is the black body. So it depends on the temperature of the source. Okay, the source that transmit the energy. Okay, it depends. So if the source is the sun or a light, okay, so it depends on the temperature of that source. Okay, so the radiation energy emitted by a black body, so it's we use the Stefan Boltzmann constant, the sigma, the sigma symbol 5.67 10 minus 8, 10 power minus 8. Okay, watt per meter square per Kelvin. Power of 4. Okay, so this is the how we characterize the radiation energy. Okay, so it depends on the temperature of the source. Okay, so a black body is said to be a diffuse emitter since it emits radiation energy uniformly in all directions. Okay, radiative properties. I think this one okay. Okay, I skip to the emissivity. Okay, I mentioned about emissivity just now. Okay, so emissivity, why this parameter is important? Okay, is the ratio of the radiation emitted by the surface at a given temperature to the radiation emitted by a black body at the same temperature. Okay, so we see here, emissivity is like efficiency. Okay, efficiency of the surface, how it can transmits radiation energy, okay, compared to the reference, which is the black body just now. So we assume that the black body is the idealized body. So if a surface can transmit all the radiation energy, so the emissivity will be 1, it's like 100%. Okay, so but here it's about normally is around 0 to 1. Okay, 0 point something. Okay, depends on the surface. Okay, so we have to know, we have to characterize each of the surface when we want to if you want to design. Okay, for example, a window, or a house, okay, with a window, we have to know how much is the emissivity of the glass, okay, of the glass used that we're going to use to for the window for our building. Okay, so because higher level of emissivity of the glass means that the glass can transmit more radiation energy. Okay, more heat, more lights. Okay, so that's why this parameter is very important. Emissivity is a measure of how closely a surface approximates a black body. Okay, so a black body will have emissivity equals to 1. Okay, 100%, like 100% efficiency. Okay, the emissivity of a real surface varies with the temperature of the surface. Of course, it depends on the temperature as well as the wavelength and the direction of the emitted radiation. So it depends, it is like a vector, it depends on the direction. Okay. So okay, so these three parameters, okay, measurement also are important for for a solar energy, to design solar energy. Okay, the absorptivity, the alpha, which measure the absorbed radiation. Okay, so how much pen ni tak work okay. Oh, tak ada battery tu lah. Okay. It's okay. Okay, so we see here. Buat dengan tangan. Right with the hand. Okay, okay. So this one. Okay. So this is the, okay, imagine this is the incident radiation. Okay, incident radiation. The notation for incident radiation from sun or any heat source, the light. Okay, we write it as G, and the unit is watt with power per meter square. So we measure an incident radiation in watt per a meter square of the surface. Okay, so for example, this is the surface. Okay, so the incident radiation in this direction. So, but not all of the incident radiation will be transmitted. Okay, transmitted to the opposite surface. Okay, for example, if we have a window, our window in our room, okay, not all of the incident radiation from the outside, from the ambient, is going to be transmit inside our house, okay, inside our room. Okay, so these parameters, alpha, rho, reflected radiation, reflectivity, and the transmissivity, okay, will measure the amount or the percentage, the efficiency of this incident radiation, how much it will absorb, how much it will be transmitted, and how much it will be reflected. Okay, so normally the total incident radiation, some of it will be reflected. Okay, pembiasan, reflection, absorbed, okay, and some of the portion will be transmitted. Only some of the portion will be transmitted. Okay, so it depends. All of these parameters depends on the material, the surface. Okay, this material, the surface that we use. Okay, so different surface, different body. Okay, different material has, of course, different absorptivity, different reflectivity, and different transmissivity. Okay, so but the total alpha, rho, and tau, the transmissivity will be equals to 1. Okay, that means that equals to the total the initial radiation from the sun, or from the sunlight outside. Okay. Okay, so for example, if we have incident radiation, the solar, we assume that the radiation at our location, Kuala Lumpur or Bangi, I'm at Bangi right now, at near our house at Bangi, the solar radiation is what? For example, I don't remember the exact amount, but for example, if we have 200 watt meter square, okay, we measure always like this, watt per meter square. So maybe like what, 20%? Okay, 20% is being reflected. So 20% is around 40 watt, okay, per meter square, and some of the amount is being absorbed, maybe 10% or more than that, I don't know, I'm not sure. Okay, so 20, so the rest 60, 40, the rest 40 watt per meter square will be transmitted. That means that is the actual value that is going to be, we assume that it is going to be transmit into the building or into our house. Okay. Okay, and okay, this one. Okay, if you have a normal body, glass, for example, the window glass, glaze, we call glazing windows. Okay. Okay, so the sum of the absorptivity, reflectivity, and transmissivity is equal to 1. But for opaque surface, opaque, what do you call it in bahasa Melayu? Macam dia macam nak gelap, tapi bukanlah totally macam black body, okay, but it's quite apa tu, macam gelap lah, kan, tak transparent. Okay, so for opaque surface, we only have absorptivity and reflectivity. The radiation, the incident, the source will not be transmitted to the surface, to the material. Okay. Okay, so the absorptivity of material may be quite different for radiation originating from source at different temperature. Okay, so it depends on the temperature, of course. Okay, next, greenhouse effect. Okay, so we always mention, if you talk about environmental impact, environmental saving, people mention a lot about greenhouse effect, but actually what is greenhouse effect? Okay, so here, greenhouse effect, glass, it has a transparent window. Okay, over 90% of solar radiation is emitted. Okay, glass allows the solar radiation to enter but does not allow the infrared radiation from the interior surface to escape. Okay, we imagine as if there is the infrared radiation, there is a radiation somehow that cannot be emits back to outside. Okay, so the radiation, which is this infrared radiation, is like what do you call it? Terperangkap, kan? Inside the house, okay, under the window, the glass. Okay, this cause a rise in the interior temperature as a result of the energy built up in the car. For example, if you are in the car, kan? If you have a car, we have the window, and this radiation, okay, this infrared radiation cannot escape, okay, to the outside, okay, cannot escape from the interior surface to outside. Okay, so the radiation is being trapped, terperangkap, trapped inside the car or inside our building, our house, right? So this is what we call the heating effect. caused by the radiation, this infrared radiation, is what we call the greenhouse effect. Okay, the energy that is trapped inside the building or the car, the body. Okay, so of course, we want to reduce as much as possible this greenhouse effect. Okay, so a lot of energy technology being designed, being research being done, particularly in order to reduce this greenhouse effect, right? Okay. So enough about radiation. Okay, so just a brief introduction, very, very brief introduction about radiative heat transfer. So actually, if this radiation or this radiative heat transfer is like one course or one chapter. But here I just a brief introduction so that you understand the process of the transmission of the solar. Okay, so because we are not in the heat transfer mechanism or heat transfer course, we are in the renewable energy technology course. So we focus more on the technology. Okay. So you can interrupt me, okay? If you have any questions or anything you want to ask, okay? Okay. Solar energy, okay. So the daily energy from the sun is 100 times greater than energy produced each day by all others. So it is assumed that this solar energy has a lot of potential because we receive, okay, the energy the daily energy from the sun, like much greater, higher than any other energy. For example, like us in Malaysia, we receive sun, okay, the light, the heat source from the sun more, the energy source from the sun equally each day, because we don't have 4 seasons like in the other countries. Okay, so we have like 12 hours direct sun, and 12 another 12 hours. Okay, and but for example, if wind, okay, we have less wind speed. Okay, so the potential of the wind energy may be less for us, but compared to the solar energy, we have more energy source. Okay. Okay, so the only problem of the solar energy that is normal, okay, not just for us. Okay, the major problem with solar energy are it's intermittent, which means that it's only available during the day, during the daylight, of course, siang kan. So when we design or when we manufacture a very research done for solar energy, we always have to take into consideration or think about how are we going to store this solar energy, because we know that we cannot receive cannot have this energy 24 hours all the time. So we have to think about the storage system, or sometimes we have to do maybe a hybrid system, solar with wind or solar with geothermal. Okay, because the solar energy is not available 24 hours throughout the day and night. Okay, that is one of the major drawback. Okay, solar energy is utilized in 3 ways: passive heating, active heating, okay, and solar energy is also transformed into electrical energy, okay, by using one of the method is by using the photovoltaic panel. Okay, so sometimes we use passive heating, means you just receive the heat from the sun, and then the heat is being converted directly at the place collection site, or at the building that the house that we want to use directly. Or sometimes it is by using another device, okay, to transport the energy, the sun's energy, and converted it into heat or power. for example, with a turbine, gas turbine, to convert the sun's energy into another form of energy, heat, mechanical power, etc. Okay. So one of them, just introduce one of them. For active heating, one of the method that me myself I'm currently in uh, currently doing the research on that, is by integrating solar PV with a cycle, a gas turbine cycle that we call organic Rankine cycle, ORC. By using the Rankine cycle is a normal thermodynamic cycle to transform the energy source to heat power. So we combine. The idea is to combine this solar PV, the solar energy source, with a thermodynamic cycle that is called a Rankine cycle. So this Rankine cycle will convert the heat energy source to mechanical, to be used in a mechanical power or heat power or heat energy. Okay. So there is one type of example. Okay. Specific light energy is transformed to heat energy when it's absorbed by a surface. Okay. Okay. So we look at this. Okay. These are some of the for a house, a building. Okay. A lot of them is a lot of the design, the technology is being implemented in Europe basically. Okay. In Malaysia, we have started, okay, but still very, compared to outside Europe, we are still at the very small usage of this solar energy source. Okay, so for example, this one is sun space storm wall. Okay, these are some of the example of integrating the solar. Normally we will use solar PV, solar panels. Okay, so okay, the A and B, the sun space and storm wall, actually that one without the solar panels means that we, instead of they design, okay, the designer, okay, they design the house, okay, with like a double glazing. You can see here, it's like it has this glaze window, another row of window, okay, two rows of windows, something like that. In Europe, they basically have this type of house, or this type of building. Okay. The sunlight, okay, the sunlight transmitted, okay, of course not all the sunlight will be transmitted inside the house, inside the building. Okay, only some portion of them will be transmitted. So that's why just now we need to know first about the radiation heat transfer. Okay, so it's only some of portion of the sunlight will be transmitted, depends on the material of the glass that is used. Okay, here depends on this material. Okay, so there's also another heat transfer mechanism, which is convection. Okay, what the process inside this area. So actually here, between the two glaze window, okay, the area between the two glaze window, we call it as as air gap. This is air gap area, air gap. Okay. Means that we don't use any mechanical power here. It's only natural ventilation. We call it natural ventilation. Okay, no mechanical power. Okay, no fan or anything. Okay, means that it is naturally ventilated. Okay. So here in the air gap, the physics, okay, the phenomenon behind is that what do we call the Beyonce force. This one in fluid mechanics, Beyonce force. Okay, so it's actually tak nampak. It's actually we assume that the density of the fluid, okay, if the fluid has a higher temperature, it will be less dense, right? The density will be lower. Okay, kalau gas kan, fluid, okay, kalau dia lagi panas, biasanya dia akan berada di atas kan. Kalau fluid tu dia lagi panas ataupun gas tu dia lagi panas, air tu lagi panas, dia akan berada di atas. Air ataupun fluid yang lagi sejuk, biasanya means that lower temperature, dia biasanya akan berada di bawah sebab dia more dense, density dia lebih tinggi, biasanya kita assume macam tu kan. So dekat air gap tu dia macam akan ada fluid tu dia akan flow, yang kita assume yang lagi panas tu dia akan naik ke atas, yang lagi sejuk akan ke bawah. So dia guna teori, okay, untuk apply dalam air gap double glazing ni, dua glaze ni, without any ventilation force. Okay, just naturally. Okay, naturally ambience tu, udara tu. Okay, so we assume so that's why this type of design, the A, okay, the sun space design is a lot used in the the country which has 4 seasons, like they have winter, for example, right? Because they don't need any forced ventilation, any extra auxiliary power, fan, etc. They save by using fan, etc. They just use natural ventilation, but by having double glazing window, okay, so they assume that the higher fluid temperature, okay, in the air gap, okay, so maknanya fluid temperature yang dekat atas tu, air yang dekat atas tu assume akan lagi panas, so sebab tu dia less dense. So yang udara yang lagi panas tu yang akan masuk dalam building, in the house, rumah tu. So dia akan heat up lah, dia akan heat up rumah tu, especially kalau time winter. Okay, so instead of dia guna heater, okay, yang biasanya rumah kat luar negara tu dia ada heater lah kan, tapi heater pun guna juga, cumanya ini extra biasanya sebab dia guna dia use natural ventilation. Okay, so the warmer air will goes into the building. Okay, so the building will get a warmer, heat up, okay, especially during winter, and the the colder fluid, okay, will be transmitted back to the outside, to the air gap and outside lah. Okay, so there is another heat transfer mechanism, which is convection. Convection dia prosesnya macam tu, convection. Dia hot and cold fluid akan exchange fluid. Okay, so the concept is like that. Okay, so they use this double glazing technology, okay, to warm the building during winter or autumn, okay, during cold weather. Okay, actually this technology can also be used, okay, during hot, kalau during hot summer or spring sometimes, okay, the hot temperature, the warmer temperature from inside the building, from inside the house, will be transmitted to the outside. Okay, so it is the opposite. Okay, during the hot weather, hotter summer, etc. So the hot fluid, okay, from inside the building, we assume that it will goes up, okay, by using this buoyancy force. Okay, so then it will be transmitted to the outside. Okay, so the convection process will continue. Okay, another one is by using thermal wall. Okay, throne wall ni instead of having two glaze, okay, two windows, double glazing, they just use one glazing outside, another one is like an opaque surface, okay, the throne wall, we call it throne wall. Okay, so the process is still the same. Okay, there is an air gap here between the throne wall and the window, the glazed window outside. Okay, so the heat from the air gap, okay, will be heated up and will be transmitted into the building and will exchange through process. Except that by using thermal wall, of course, uh, the temperature, okay, the ambience, the temperature will be higher because thermal wall, like we know just now, it it absorb more radiation from the sunlight. Okay, it's like an opaque surface. Okay, okay, this and then solar home, okay, example of solar panels on top of the roof. This is quite common. Okay, even in Malaysia sometimes we have this. Uh, okay, example active solar heating design. Okay, so this is example of the house. If they or school room, they use solar radiation. Okay, for a solar collector. Okay, the heat from the sun here. Okay, this is the source, and they use solar collector. I will show you later on in next slide. The process in the solar collector, solar thermal collector. So this solar collector has a PV photovoltaic panel. So it will absorb heat and convert the heat, and the heat will be used and pumped to water radiation here. Okay, so we can use the hot water. Okay, inside the room, the school, or in the building. Okay, so the hot water uh, uh, the source for the hot water is from the solar. Okay, this is example of the process. Okay, means that we have the energy source here is the heat, and then we have pump to pump the fluid. Okay, the heat to be used in the for example here in schoolroom or in the toilet for solar heat water. Okay. Solar energy can generate electricity in two different ways. Still can be created to drive a turbine. So, okay, this one is like just now, active and passive. Okay, photovoltaic PV panel. Okay, so when we talk about solar energy, I'm sure you are familiar with this photovoltaic cell. So, of course, we have to talk about photovoltaic cell. So photovoltaic cell is a solid state semiconductor that converts sunlight directly into electricity. Okay, so when we apply this solar PV panel, so actually a lot of fundamental knowledge has to be integrated. Okay, there is electricity part, how to convert the semiconductor to electricity, of course. So we need electrician from electrical background. And then how do we convert this heat to power or mechanical power, right? That one is the from mechanical background. And sometimes the material that we use in the PV, okay, there are different types of material that can be used for the cell of the PV. Okay, that study or knowledge also is a lot is being used by researchers from the chemical background. Okay, because they study the mechanism of the materials transfer between the inside the photovoltaic. Okay, so actually me myself, my area is more on the heat transfer. Okay, the mechanical part. Okay, but of course it means that we cannot work by our own self. Okay, as if you want to design something uh, that is more complicated, bigger technology, we have to integrate all of this knowledge, all of this technology, all of this fundamental knowledge. Okay, the amount of PV power installed worldwide has increased. Okay, so it keeps increasing. One of them is thin film technology. Okay, thin film technology has made it possible to build solar cells into roof shingles and tiles, building facades, and the glazing for skylights and etc. Okay, so one of the type method of solar PV energy is thin film. Okay, there are also other types. Okay, we see. So this is a photovoltaic power plant at a location, I'm not sure where. Okay, so if we have at one site power plant. Okay, these are all photovoltaic power plant sites. Okay, this one. So okay, so a PV photovoltaic modules. So actually, it is sometimes we have to differentiate. Okay, the meaning of PV cells when we mention about PV cells, PV modules, or PV arrays. Okay, so these are different what do you call it, different term for a photovoltaic. So a cell is the one, the small, okay, rectangular one. Okay, this is all cell. Okay, okay, this is what we call PV cells, photovoltaic cells. Okay, a module, a a photovoltaic module combine all those cells in a panel. Okay, in a panel, something like that. Okay, so for example, here we have 1 2 3 4 1 2 3 4 5 6 7 8 9 9 ke? About around 9. So 9 times 4, 36. Okay, so for one module, for example, here in this photo, in this figure, one module, okay, to design a PV module, we need 36 cells. Okay, 36 cells to design one PV module. So that's why when we mention about the price of PV cells, so we have to combine. Okay, we have to calculate how much total up all the how much the PV cell that we need to be used in one module. And for one array, one PV array on a rooftop like this, okay, how much a total of PV array do we need for a house, for a rooftop like this? Okay, so for this one, like, we need 8 PV arrays. Okay, so 8 PV arrays times 36 just now. Okay, I'm not sure how much. Okay, so means that there's a lot. Okay, a lot of PV cells need to be used. Okay, for just one installation on a rooftop. Okay, so at least you understand here the different term: PV cells, PV module, and PV array. Okay. This one. Okay, so this is on the left hand side. My right hand side is the module, and on my right hand is the is one cell. Okay. So the characteristic of a PV cell are measured according to the standard test condition. So we just write it as STC. So when we say STC, okay, it means standard test conditions. Okay, so when we purchase, okay, we want to purchase PV cells, okay, or PV modules, we need to know this condition. Okay, so incident radiation of 1000, the temperature, the air velocity, solar spectrum of mass 1.5 spectrum. Okay, so those are the standard test conditions for PV cells. Okay. CSI is the crystalline. Okay, crystalline monocrystalline or polycrystalline. Okay, we see the, okay, commercial PV materials normally use monocrystalline or polycrystalline cells. Okay. So amorphous, there's also thin film technologies like I mentioned just now. Okay. Okay. But however, okay, the price of the polycrystalline silicon, okay, have led to many solar cell manufacturers to seek alternative raw materials. That's why, because maybe you see some of the research are done or currently being done in order to seek for other materials for PV cells. Okay, because of the high price of this silicon, crystalline silicon. Okay, so one of them is thin film module. Okay, so thin film module are made from also silicon, as amorphous silicon, cadmium telluride. Okay, all those chemical material. Okay. Okay, but however, solar polycrystalline or monocrystalline are still being used a lot. Okay, major use by designers. Okay, because the process used to make polycrystalline silicon is simpler and cost less. Okay, okay, so those are the types of PV cells. Okay. Okay. Solar thermal collector. Okay. So normally the PV panel is being integrated with a collector that we call a thermal collector. Okay, so that we can other than transform other than just transform the heat from the sun, the radiation from the sunlight, we can also produce heat. Okay, heat inside the collector. So that's why it is called solar thermal collector. So basically, what do we have here? Okay, this is the schematic diagram of a solar thermal collector. So basically, if we have okay, so this one is without PV. There's also solar thermal collector including PV. Okay, but we will see first the one without PV. So just solar thermal collector. So it is like the double glazed house just now. Okay, so the air inside the collector, okay, it's like the air gap inside the double glaze just now. So here we have the glass cover. Okay, the glass cover, and of course also the direct radiation from the sun. So the sun will transmit, some of the portion will be transmitted, okay, into the collector, inside the collector. Okay, the air inside, there is air inside here. Okay, or sometimes they use other types of fluid. Okay, if they want to if the fluid is normally if the fluid have higher conductivity level. Okay, for example, they can use nano fluid. Okay, but the initial one, okay, the general one, conventional one is the air. Okay, so there is air inside the collector. Okay, so the heat transmits from the radiation, the solar radiation. Okay, will cause heat. Will cause the air to be heated up. Okay, so there is convection process inside. Okay, some of the radiation will be reflected also. So the heat produced by the collector, okay, will be those available heat that will be used for the building or any or for other device. Okay, so means that by using this thermal collector, we trap the energy from the sun inside the collector. So when the air is trapped, usually the fluid will be warmer. Okay, so when it becomes warmer, absorb more heat, the available heat will be greater. The thermal energy will be greater, will be bigger. Okay. Uh, okay, so this is the main process of a solar thermal collector without PV. Okay, despite the air thermal collector has lower heat capacity and lower conductivity compared to water thermal collector. Okay, sometimes they use water also inside the collector. It is mostly applied in general if there is a demand for hot air, space heat. Okay, means that this solar thermal collector can be used for space heat, of course, for in a build like in a building just now. It can also be used for agriculture. Okay, agricultural products to dry the food. Okay, or to condition the indoor air cooling, okay, like just now, due to its advantage, which has no freezing or boiling of collector fluid and no damage if leakage occurs. Okay, so this solar thermal collector also have been used, okay, widely. And then, okay, these are the types of some of the types of the solar thermal collector. The first one is the flat plate collectors. So flat plate collectors. So the heat from the sun, okay, will arrive here and will be absorbed, and we have water or air inside or other fluid inside the collector. Okay, evacuated tube collectors, different tube. Okay, so it will exchange heat. Convection also will happen here between the tube and the air or the fluid inside the tube. The tube ni ada tube, ada banyak-banyak tube. So imagine ada dalam setiap tube tu ada air ataupun water yang akan lalu dalam tube tu. So kat situlah dia akan berlaku convection heat transfer. And this is a parabolic Parabolic is like a concentrated sebab dia macam concentrate bila dia when the surface macam convex concave melengkung macam tu, so dia macam concentrate the energy radiation from the sun to be concentrated at the surface parabolic macam tu. Kita guna surface parabolic. Okay, I think we take a break now. Dah azan maghrib. Okay, we take a break now. So we will resume at around 7:30. Okay.
Okay, doktor.
Yeah, dah azan.
Okay, doktor.
Let's stop recording. InsyaAllah maybe you continue until azan isya tu, tak ada masalah insyaAllah. Okay. Okay, all here. I continue all class.
Ya, doktor.
Okay, so just now, before we took a break, we see the different types of solar thermal collector. Okay, okay. So now, about the building integrated photovoltaic. Okay. So, one type of application, okay, for solar photovoltaic, solar PV, and solar thermal collector is the building house types of building. Okay, so this is what we call building integrated photovoltaic, or simply BIPV. Okay, so when we mention BIPV, we understand that it is about building integrated photovoltaic. Or sometimes when it also has a thermal collector, solar thermal collector also, when we also integrate the solar thermal collector, we call it as building integrated photovoltaic thermal, BIPVT. Okay. sepanjang ya. Okay. So rather than in a type of solar cell technology, we have this technology which is called BIPV. Okay, so this is based on sometimes it will be crystalline base PV panel or thin film solar cells. Okay, so the building integrated photovoltaic can be facets. Facets is like the at the window somehow the wall. Okay, window wall, roofs, windows, walls again, and many other things that are combined with photovoltaic material. Okay, so the advantage of an integrated this PV air collector, solar thermal collector, to the building are better architectural appearance. Okay, so one of them is for aesthetic. Okay, a lot of the building which has solar PV integrated with the building. Normally, it is designed. The design is very beautiful. The architecture design is very like with beautiful appearance. So it has that aesthetic design. Cost decrease. In addition, the distribution and storage can benefit from the building structure. So as we use like the example that I showed just now, where we combine the PV panel, okay, use the solar energy from the PV panel, and at the same time with the solar thermal collector heat. Okay, so we can produce heat, power and electricity at the same time. Okay, so it's like a hybrid system somehow. Okay, the collector can also perform the function of anti-noise barrier. Okay, it can be also as anti-noise barrier because since it is like a double glazing, okay, double wall. Low response time, the collector can hit a room as soon as the radiation appears. Okay, the collector can form a buffer zone. So it depends on the, of course, depends on the solar radiation. Like a buffer zone, the air gap just now. And the ventilation control system is simple. Okay, it's quite simple. Okay, so this is the schematic cross section. Okay, like the diagram that I showed just now. So we have the PV cell. Okay, here we have a PV cell instead of just glazing a glazing window. We have a PV cell here. Okay, this is a PV cell. Okay, so but the process is the same. Okay, so we have the radiation from the sun from the outside. Okay, will be some portion will be reflected and some will be transmit into the air gap here. Okay, the air collector. Okay, so there will be some of the heat produced, transformed. Okay, so this is what we call a building envelope. Okay, the solar thermal collector is what we call like a building envelope. Okay, because it is like a double wall. Okay, so the heat, the portion of heat transfer into the building. This is what we are going to measure. Okay, when we want to measure the performance of the energy balance of the building. Okay, we want to measure the heat that actually available and transmitted into the building that will be used. Okay, okay, this is another schematic diagram, okay, of the air thermal collector. Okay, so the air will be introduced. Okay, we will enter. Okay, the collector from below. Okay, so we assume that the less dense. Okay, like just now, the less dense with less density air fluid will goes up, okay, to the at the top of the level of the air collector, and the colder, okay, the lower temperature of the fluid uh, will be at the bottom. Okay, so the higher temperature, the warmer air will enter the space inside the building that we want to heat or want to warm. Okay, different types of buildings integrated photovoltaics. Okay, so there is shading, integration, like not really like not like kind of like a rooftop, but it's a shading, actually shading integration or veranda integration, like a posh though. Okay. There's also roof. Okay, the typical one roof. Yeah, this one is the facade integration. So nampak cantik kan? So that's why somehow in a maybe not for a house, but for office building or hotel, they tend to, especially in the uh, in the European country, overseas, they tend to use, okay, this facade integration, because aesthetically it is very very design very beautiful. Okay, window sill integration at the window. Okay, this is like a window. Some university buildings, my university building, before this, we have this window sill integration of PV photovoltaic. And this one's, actually this photo was the double skin integration. Okay, this was my experiment during my PhD. Okay, so this is the prototype that our team has done, double skin integration. Okay, so okay. Actually tak banyak dah slide saya, sikit je. Okay. So this is to summarize the integration types, the types of integration of BIPV which are available. So there is a roof. Sorry, a bit small. The writings. Roof. Okay. So normally roof. The roof integration without air channel means that there is no air collector. Okay, when we apply the roof integration, like just now, this one. Okay, this roof integration, there is no air gap. Okay, between the PV panel and the rooftop. Okay. Facade. Okay, facade and window sill. There is with and with air integration, but ventilated or unventilated. Okay, means actually the unventilated is actually natural, by natural ventilation, means by natural um, uh, natural ventilation, udara luar je. Okay, kalau but with air channel ventilation, ventilated, so sometimes we have a ventilator like a fan. Okay, this process what we call forced ventilation. Force means that we put auxiliary power to force the ventilation in the air gap, air channel collected in the air collector just now here. Okay, sometimes when there is a ventilator, okay, here, okay, to force the airflow, so that the air will be the speed of the air entering the process will be quicker, okay, faster. Okay, but of course it needs use when we add force ventilation, we use more power. Okay, input power. Okay, so integration with, so for facade and window sill, there is with ventilation or without force ventilation. And there is also chimney BIPV, building integrated photovoltaic with by chimney. Veranda, okay, veranda is with air channel and ventilated. Shading PV shading. Okay, so those are the types of the integration of PV solar panel for building. Okay, so BIPV. Okay, so I just have a 2 page left. Okay, so actually, okay, so this one, so I just share some of my so I share my paper. Okay, I share my some of the research that I have done before. There is this one is during my PhD, so it was 5 years ago, and this one is quite recent, last year. But actually, it is the continuation and application of this of my PhD thesis actually. Okay, so I just would like to share this one with you. Okay, so it was about simulation study of a naturally ventilated building integrated photovoltaic thermal, panjang, BIPVT envelope. Okay, envelope because of the double wall, double wall just now. So sometimes we call it double wall, double wall, or sometimes we call it envelope. Okay, the term envelope, building envelope, is quite widely used. Okay, simulation study of it. So the prototype, okay, the prototype is the photo just now that I show you guys. Okay, this is the prototype experimentally being done at a site location at the south of France at that time. Okay, so me, I did the simulation modeling and simulation part. Okay, by using a thermal building software called Transys, TRNSYS. Actually, there's a lot of other software available, also energy software. But one of the is Transys. Is just that Transys is not free, paid, and it's quite expensive actually. But the function in the software is quite useful. Okay, for especially to study energy, renewable energy technology, other than solar energy, geothermal, even ORC, the organic Rankine cycle I mentioned just now. So Transys can be used. Transys software, this thermal building software can be used to simulate, to model and simulate the energy balance of this all of this process technology. So this was about so I've created I've model the double glazing the double glazing naturally ventilated photovoltaic panel with the solar thermal collector. And I've integrated also the by using semi-transparent PV panel. So at that time, the semi-transparent PV panel was still new. Okay, somehow. Okay, so to model that semi-transparent panel, I needed to create like a numerical model. Okay, a new numerical model. So that is one of my objective of my PhD. So what I want to share with you. Okay, so this is the schematic diagram of the double glazing wall building. Okay, so the PV panel from here. So we need to take into consideration all uh, of the process of the radiation from the sun when it transmitted. What is the transmission parameter, the absorptivity of the PV panel. Okay, since it is semi-transparent, means that it's there is a percentage of some percentage of PV panel, and there is some percentage of glaze. So dia macam campur glaze instead of all of them over the panel PV, tapi dia macam campur glaze dan PV. So dia punya portion yang kita kena take into consideration lah. Okay, so to model the air collector, ni air collector dia. Okay, so I divided the air gap into several zone. So this zone is actually a virtual zone. Kan macam kita imagine lah ada zone kan, so that we can easily it is easier to solve the energy balance inside the air collector. So so macam itulah. So we take into consideration the radiation, the convection, especially the convection inside the air thermal, and also the conduction in the wall. Okay, so because the heat from the air from the thermal collector will be transferred to the interior building. Okay, so we need to understand well properly the energy balance, the energy performance from the solar radiation and then the air thermal collector before we can conclude how much the energy that actually being transmitted to the building, and how much actually the energy needed, the heat needed by the building for the building to keep warm. For example, if we want the building to be at from 7 a.m. to 12 p.m. We want to keep the interior building at 27 degree, for example. Okay, so we need to calculate. We need to design the solar thermal collector with the PV panel that can produce, that can give heat, okay, the air that has a temperature around 27 degrees Celsius. Okay, so that is the purpose. Okay, at certain time, at certain period of time, maybe at in the afternoon or in the evening, the energy needed or the temperature needed will be different. Okay, so that's why there is that is the critical part. Okay, for a designer, we need to design uh, the most suitable, okay, the most suitable technology, the most suitable solar thermal PV collector that is can be used for this type of building. Depends on the types of building as well. Depends on the occupants, how many occupants that we have. Depends on the surface area of the building. So there's a lot of parameter that need to be taken into consideration. Okay, so this part, okay, this part is the heat transfer part, the process of the heat transfer mechanism from the exterior air, ambient, okay, and PV panel until it reach TZ. This one is the building wall. Okay, so for an engineer, okay, you guys, okay, when in order to design or to select which technology PV, if you want to use solar PV, uh, if you want to design, then you need to take into consideration all of these parameters, okay, the energy balance that we have to measure, we have to calculate, so that we can know how much energy that actually being transferred to inside the building. Is it enough, or is it we need to use to provide more heat, okay, to use more PV panel. Okay, so this is the energy balance. Other than that, this another paper by me also. So, but this one is more on the analysis part, application analysis. So if you remember, during the first week of the introduction of the course, I talk about the second law of thermodynamics, right? Second law of thermodynamics, which involves the entropy. Entropy is the parameter that we use to measure the second law of thermodynamics. The first law of thermodynamics was enthalpy, okay, energy. Second law is entropy, to account for the irreversibility or the energy loss in the process. Okay, so exergy here, exergy, okay, exergy is a parameter also used for second law of thermodynamics, this entropy. So actually exergy and entropy is quite the definition is the same. It's just that when we want to use it, okay, but because the unit is different, but the function, the objective is the same. Is exergy and entropy. We want to account for the second law of thermodynamics, the energy loss, the irreversibility. So we apply this exergy analysis concept or entropy loss, energy loss concept in the BIPVT. Okay, so to analyze, it is to analyze when we have created the BIPVT system by using natural ventilation here. When we created the BIPV, and then we analyze it by calculating, measuring those parameters: energy, economy, environment. Okay, those terms are actually based on the energy. Okay, remember when I said that the second law of thermodynamics is measure the useful energy being transferred, useful energy being produced. Okay, so when we want to measure the economic impact or environmental impact, it is better to calculate those impact based or in terms of this SG, this second law of thermodynamics, instead of based on the first law, enthalpy, energy. Okay, because when we measure it, we analyze it based on the second law, entropy or SG. It is more accurate because we only take into consideration the actual energy being used, the actual energy being produced. Okay, so that's why some researchers studies, or me myself, I've done the analysis based on the second law instead of based on the first law. Okay, because it is proven to be more accurate in order to take into account the impact on the economy or on the environment, the carbon dioxide emission, etc. Okay, so the figure here, like just now, okay, but it explained better, okay, on how the BIPVT system with natural ventilation, and the other one with forced ventilation, I mentioned just now, natural and forced ventilation. Okay, so the natural one, the fresh air will goes into the thermal collector or the air gap. Okay, the fresh air will enter the air gap. Okay, so and the hot air that we assume has less density, higher temperature, so has less density than the fresh air, so it will go uh, will be thrown outside. Okay, will go outside, whether to the exterior in hot summer, in hot weather, or the hot air will enter the building, okay, if needed for winter weather. Okay, but usually this technology, natural and forced ventilation, in European country, they use natural ventilation concept during hot weather, summer, and forced ventilation is used usually in the winter, cold weather. So because we can force the hot air from the air gap, we can force the air from the air gap, okay, to be ventilated with the fan, and to be transferred inside the building indoor space, so that we can heat up or warm up the indoor space inside the building. Okay, so there is the difference between natural ventilation. Of course, with natural ventilation, since we use only natural source, so we don't need extra effort, extra auxiliary power, extra electrical power. Okay, but somehow is of course it is quite slow because it depends on the nature. Okay, but by using forced ventilation fan, so we force the ventilation process. Okay, the air, we force it into we increase the speed, the kinetic energy, the speed of the air, the convection. Okay, so it will be faster, so we can have a more warmer temperature inside the building, but it needs, of course, it use more electricity. Okay, left, okay, figure 3 of this figure on the right hand side is to explain the semi-transparent and the opaque PV module that I mentioned just now. Okay, sometimes we use semi-transparent or sometimes we use opaque. There is pro and cons. Okay, if you use semi-transparent, there some of the radiation will be transmitted, okay, to the inside the building or inside the space that need the that we use for indoor space. And or for PV module, it is like a back sheet, okay, back sheet. So it's like a black body, okay. So the radiation is the heat from the sun is being trapped inside the solar thermal collector, the air collector, okay. So we have sun, glass, glazing, and then encapsulation. EVA is the material. Apa dia punya nama? Ethylene something. Okay, is the name of the material used for encapsulation of a solar cell. Okay, because to keep the supaya nak menjaga the PV cell. Normally the PV is being encapsulated by another material, uh, which usually we use this EVA material. Okay, solar cell and a backsheet. So there are two types of PV module, PV cell. Okay, opaque or semi-transparent. Okay. 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 In this slide, for today, I'm not showing yet the results of my research. I will show you in a future chapter, because we are going to continue this chapter on solar energy and the application of this PV to building, or this renewable energy to building. We will continue in the next next few chapters. So we are not finishing yet. So I will show the results or the findings in the next chapter, inshallah. Okay. So just sharing with you guys some of the study that I have done for this technology, solar technology. Currently, like I mentioned just now, I'm also try to study application of using solar PV thermal collector with the thermodynamic cycle that I mentioned just now, Rankine cycle, in order for to produce heat and mechanical power at the same time. Okay, so I'm currently doing research on that. Okay, so so I think that's all for this introduction of solar energy. So actually it's already okay. I resume back, summarize back the content of this chapter. So at the beginning just now, we look at the process of the transmission of the solar radiation. Okay, so basically the transmission of the solar energy from the sun to another form of energy. It applies the radiation heat transfer process. Of course, after that, there is also convection and conduction, like the solar air thermal collector just now. We use convection heat transfer also. But the first part, okay, from the sun to to another form of energy to transform the solar radiation. Okay, so it use the radiation heat transfer effect. Okay, electromagnetic waves radiation. Okay, thermal radiation. So everything around us constantly emits thermal radiation. So that concept that we have to understand. And then black body radiation. Okay, because we want to compare, black body is like the ideal body. Okay, the ideal body that can absorb all the heat. Okay, all the radiation. So it is like a reference base for other different bodies material. So from this black body that we can measure the emissivity parameter for each surface. Okay, so for glazing, for any material, any solid material, they have emissivity value, which depends on the black body just now. Okay. Uh, Absorptivity, reflectivity, transmissivity. This especially when we want to apply a semi-transparent material like a glass. Okay, so glass can absorb, at the same time it can reflect back the solar radiation, and it can transmit also the radiation. So these are the parameters that we have to know when we want to choose types of materials for glazing, for example, okay, for building. So for each material glass, usually they has different parameters: absorptivity, reflectivity, and transmissivity. And greenhouse effect also, solar energy. And then I explained just now about the building integrated photovoltaic panel. Okay, the cell, modules, and arrays. Okay, the different term that we use for PV cell, PV module, PV array. Solar thermal collector, different types of solar thermal collector, different types of integration of the BIPV system, and just sharing some of the findings that I have before this. Okay, I think that's all for this week. InsyaAllah, anyone want to ask anything, any questions? Okay, Anas, Ajin, Ashikin, Safraisa.
Dr. Anas here.
Yeah.
For solar energy, is there any impact on the environment? Is there any issues on environmental impact? Is there any negative impact on the environment?
Yes, of course.
Okay.
That one memang ramai lah, ada juga yang memang ada study juga on that particular area. Of course macam ni nak dispose lah kan benda-benda ni kan. Itulah masa conference yang hari tu yang saya dah pergi tu, memang kalau masa tu TMB yang tu, mereka memang ada tengah discover teknologi untuk dispose this PV cell appropriately lah, supaya dia tak mencemarkan apa semua lah kan. Maknanya macam before this memang antara isu jugalah, drawback bila kita guna PV ni, selain pada cost apa semua tu, dia tak boleh simply be thrown away lah kan. So dia impact lah kepada environment. But there are more and more research being done untuk macam mana nak overcome lah this problem lah kan, untuk so that PV, the use PV will takkan impact lah, mencemarkan environment tu. Memang maknanya macam to answer dia, memang dia asalnya dia memang ada impact, tapi kita ada usahalah untuk overcome the impact tu.
So impact dia untuk waste management je lah.
Waste management tu lah.
Okay. PV tu biasa berapa lama dia punya life?
Depends lah, gitu saya tak ingat sangat. Okay, dia punya sebab actually dia punya efficiency pun kalau macam yang biasa yang macam polycrystalline tadi dia belas-belas percentage, tapi kalau macam thin film model tu dia boleh sampai 20%, 30% jugalah dia punya efficiency tu. Dia punya berapa lama tu kan, ada certain tu boleh 5 tahun, 10 tahun juga, depends on the types of the material lah, PV cell tu yang kita guna tu.
Okay, betul.
Sebab
pendek
ada kristalin apa semua.
Pendek jugalah umur dia.
5
tahun. Okay, betul.
Itulah kita sentiasa research kan untuk replace the material yang kita guna dalam PV tu kan, yang boleh ada jangka hayat yang lebih lama lah. Okay.
Doktor,
Ya.
yang panel tu dia punya lifespan bergantung pada saiz ataupun bergantung kepada the consumption of energy yang dia mampu tampung lah.
Okay, kalau daripada bidang saya kan, dia ada area dia kan, berapa banyak area yang dia tadi tu yang PV ni kan. So biasanya macam kita kena tahulah satu sel tu dapat produce berapa banyak lah kan electricity kan. So berapa banyak kita nak guna tu lah kita akan sesuaikan lah dengan berapa banyak yang kita perlukan. So it depends on the material juga tadi tu. Sebab tu ada efficiency, different types of material. Kalau kita guna crystalline ke, kita guna thin film ke apa ke, the efficiency dia berbeza-beza. So semua tu campur-campur lah. Maknanya size dia juga, area dia kan, is the area and the efficiency of the material used. Material PV tu.
And then energy yang stored in the storage tu kan,
yang mana?
how long dia boleh simpan energy tu?
Storage depends apa tu? Kita biasanya okay, yang tu bahagian thermal storage lah. So kalau kita guna thermal storage tu misalnya dekat rumah untuk apa tu depends on the battery yang kita pakai. Dia boleh tahan berapa lama lah. Biasanya untuk macam kegunaan kalau macam untuk building seharian tu untuk malam kan bila tak ada sumber cahaya tu, so dia depends on the battery itulah yang untuk kita store thermal storage tu. Macam tu lah, lebih kurang. Okay. Ada lagi tak? Ini Okay. Okay, kalau tak ada show sampai sini lah kot, insyaAllah. Okay, untuk kelas hari ni insyaAllah. So we see each other next week lah. Okay.
Doktor, next week yang kita kena bentang assignment tu kan? Untuk pembentangan tu berapa lama
kita tak ramai, mungkin 15 minutes pun okay. 15 to 20 minutes. Kita bincang, discuss lah.
Okay doktor.
Okay. Thank you very much. Okay, that's all. Okay, insyaAllah. Okay. Thank you very much. So we see each other again next week. Okay. Stop recording.
Okay, terima kasih doktor.